The first group of molecules that we're going to look at are what are called the hydrocarbons. The simplest kind of hydrocarbon are the alkanes. So for example, I have one here, just propane, CH3, CH2, CH3. I have the skeletal structure on this side. And these are just composed of carbon and hydrogen. There are no heteroatoms, only sigma bonds, no lone pairs. And so really there are no sites of electrophilicity or nucleophilicity. In other words, there are no acidic or basic sites, and really alkanes are rather unreactive. We can burn them so they can undergo combustion, which is what we do with the gas for our cars, and we use the energy, the heat that's released to do work. And we can use alkanes for their physical properties a lot of times for waxes or oils and things like that. But in terms of reactivity, they're rather inert. The next group of hydrocarbons are the alkenes, and these are molecules that contain a double bond. So for example, I have propene here, so notice the difference this time. It's still 3 carbons long, but there's a double bond inserted in the middle here. Here's the skeletal structure. These have no heteroatoms, no lone pair electrons, but they do have pi electrons. So alkenes can be nucleophilic, as they have these reactive pi electrons. Finally, we have the alkynes, which are a group of molecules that contain a triple bond, a carbon-carbon triple bond. There are no heteroatoms, no lone pair electrons, but there are pi electrons. So again, they could be nucleophilic because of this. And I also wanted to note that when you have a proton on the end on this sp carbon, the pKa is 25, so they can have acidic protons at the terminal position. The last group of compounds that can fall into this category of hydrocarbons are the aromatics. An example of this, the most common one that you will see, is benzene. And you won't really study the chemistry of benzene until a second semester. So for now, you just need to recognize that when you see a structure like this, it's cyclic and it has alternating double bonds and single bonds. This is an aromatic compound. And of course, the formula for benzene would be C6H6. We'll talk more about that in the chapters to come. There are pi electrons, so benzene and benzene derivatives can be nucleophilic. So all of these compounds belong to a class called the hydrocarbons, and as you can imagine, the name comes from the fact that there's only carbon and hydrogen present in the structures. In terms of intermolecular forces, or IFs, as you may remember from general chemistry, hydrocarbons really only exhibit dispersion interactions. The textbook may refer to these as van der Waals interactions. Sometimes you'll see them described as London dispersion forces. But basically, this should be something you remember from Gen Chem, but just to refresh your memory, if you have a hydrocarbon like the one I'm showing here, what I'm outlining is sort of, you could just think about the electron cloud that's surrounding these atoms here. And when you get 2 of these hydrocarbons side by side, what happens is the electron clouds naturally want to repel one another, and so you start to get a let's say this has a delta negative charge all the way across. It's going to be repelling on the other side, kind of squishing the electron cloud over to give that other side a delta plus charge all along the surface. And so then you get the interaction between the delta plus and delta minus, this electrostatic attraction. But these kind of interactions are, this is what we describe as dispersion forces. They're very fleeting, the instantaneous reactions that are interactions that are always changing. You can think about this electron cloud being sort of like the surface of a bubble, and the bubble is kind of always wiggling around, and you're getting different parts of the surface area interacting at any given time. However, they can be fairly strong interactions when you add up, when they're the summative force of these. And so what we want to look at is how does the shape of the molecule change the amount of dispersion that can take place, and that will have a direct effect on some of the physical properties like boiling point. And so if we take a look at the example that we just gave, looking at the dispersion forces between two rather long hydrocarbon chains, so this is a 6-membered hydrocarbon chain, alkane specifically, compare that to this set of 6-membered hydrocarbon chain, and notice that the shape is different, right? And that means that the electron cloud around this hydrocarbon is going to be a different shape as well. It's not going to be as elongated, it's going to be a little bit more compact, and therefore the surface area that's available to interact is reduced. And so the bottom line is that the more spherical or the less elongated the shape of the molecule is, the less dispersion that will take place. And so the consequence is that even though that these are both composed of 6 carbons and then the corresponding number of hydrogens that goes with that, you're going to have a lower boiling point in this isomer of a hexane than you would in the isomer up here, because there's more dispersion that can take place. I want to make a note that you're going to start seeing this notation where R is used as a symbol. So when you see a symbol like this on a carbon, it's telling you that there is some carbon-containing group, a carbon-containing group of some sort. That's what the R is representing. So that can be any number of things, but we will use this notation all of the time in this class.